So I've left the proofs of Engel's theorem and Lie's theorem until today. So I've written out again the statements of the two theorems, and so the most of the work today is going to be proving these. Actually, as I was looking at the statements, I realized I stated corollary 2 to Lie's theorem incorrectly. It's what I had in mind, but I should have put the words finite dimensional in there. That's crucial in the statement of that corollary. I think, for example, you could look at the three-dimensional Heisenberg-Lie algebra, which we saw before. And if you remember, the universal enveloping algebra of the Heisenberg-Lie algebra has the first Weyl algebra as a quotient. And of course, the first Weyl algebra has its infinite dimensional irreducible representation. So you see that three-dimensional Heisenberg-Lie algebra has an infinite dimensional irreducible representation, but the Heisenberg-Lie algebra is nilpotent, so it's certainly solvable. So it's crucial that you put finite dimensional in the statement of that corollary 2. The proof, of course, used Lie's theorem, which went via the assumption that V was finite dimensional in the beginning. Okay, so let's go ahead and start proving these. I want to put all these proofs together because they're kind of quite similar. But let's start with Engel. So the setup here, I'm going to assume that my G is non-zero because it's trivial if it's 0. And it's a subalgebra of GLV for V of dimension n. And I'm assuming that all elements of G are nilpotent endomorphisms. Of V. So the main step in this proof, we're trying to construct this basis on which G acts strictly triangularly. The main step actually is just to show that there exists a non-zero vector in V on which G acts as 0. So given that, let's just see how the proof goes. So given that we've done that, so then you just do some induction on n. So you let V1 be that given vector V from the main step, and then you apply induction you look at the image of G in its representation on V prime being V factored out by the span of that vector V. And so when you do that, you get a basis for V prime on which this image of G acts strictly triangularly. And if you just lift that basis back to V, you get, we've already got V1, but lifting the basis for V prime gives you the remaining vectors in a basis for V, so that, well, G of V1 is 0 already, and then G of these later VI's is going to lie in the span of the earlier VI's, or possibly V1. And that's exactly what you need to prove Engel. Okay, so given the main step, it's just an easy induction on the dimension of V to finish off the proof. So now we have to prove the main step. And we're going to do this by induction on the dimension of the Lie algebra G. So I guess the base case, well, you could actually do G equals 0, but I've said G is non-zero at the beginning. So let's do the case when the dimension of G is 1. Then you just pick your V to be any eigenvector Right, so since dim G is 1, G is just spanned by some element x, and you just pick V to be any eigenvector for x, as x is a nilpotent endomorphism of V by hypothesis, the eigenvalue is necessarily 0, so xv equals 0, and that does the job. Okay, and so then for the induction step, so now we're assuming the dimension of G is bigger than 1, and what we should do is let's pick a proper subalgebra, n of G. Let's say it's a maximal proper subalgebra. Okay, so that just pick such a guy, and what we're going to do is we're going to consider the adjoint action of this n on G. So that gives us a representation of the maximal proper subalgebra n, a Lie algebra homomorphism to the general linear group GL of G. So for x in n, add x. So actually, you can just write it as lambda x minus rho x restricted down to G, where lambda x is the endomorphism of GLV defined by left multiplication by x, and rho x is the endomorphism of GLG defined by right multiplication by x. Right, and then that lambda x minus rho x, that's exactly what add x is, but I'm thinking of add x as being an endomorphism of the subalgebra G, not all of GLV. So it's add x is lambda x minus rho x restricted down to this subalgebra G of GLV that we're given. As X is a nilpotent matrix by hypothesis, and so lambda X to the n and rho X to the n, they're both just 0, right? Our V is n-dimensional here. So these nth powers of nilpotent matrices in GLV, so nth power means under composition, they're just 0. And also lambda x and rho x commute. So given those things, it's very easy to see that lambda x minus rho x to the power 2n is 0. This shows that add x is nilpotent. Great. So then I'm going to look at the induced representation. I'm going to call it just add bar. So not n acting on G, but n acting on the quotient of G by n. Right? So so n is acting on G via add, and it leaves the subspace n invariant. So there's an induced action on G over n. So I'm going to just call that add bar. And now you apply the induction hypothesis to the image of n under this homomorphism. So, right, the dimension of n, hence certainly the dimension of the image of n, is smaller than the dimension of G. So we're smaller dimension, we can use induction. And we just checked that for every x in n, add x, so certainly add bar x, is a nilpotent endomorphism. So we're in the right situation to apply the induction hypothesis. And so we get a non-zero vector in this vector space, which is killed by n. If I just pick a lift back upstairs in G, we get a vector, let's call it maybe y. So that's a vector in G, but not in the subspace n. So when we act with this add, so that's just taking the Lie bracket with n, it's 0 in G mod n, so that just means that that bracket n of y lies inside n. But then what have we got? We've got n, and we've got this other vector y. So that's a subspace of G. It's strictly bigger than n. And this condition right here tells us that this is actually a subalgebra of G. So this is a subalgebra of G, but we assumed that n was maximal. It was a maximal subalgebra. So actually, G equals n direct sum Cy. Okay, now we're just about there. So now what I want to do is I want to let W be the set of all vectors W in V such that NW is 0. And this is non-zero by induction, this time applied to n acting on V, right? And n is of dimension smaller than G. So here's this, this non-zero subspace of V on which n acts as 0. As the bracket of y and n lies in n, W is actually invariant under the action of y. So this is not too bad. If I take let's actually check that. So let's take W in W, and we'll take some x in n. What I've got to do is I've got to show that if I hit W by y, that that's still inside this subspace big W, so I have to show that x of it is 0. But xyw is the commutator xyw plus yxw, and xw is 0 by the definition of capital W. And look, this commutator, that's just another element of n, so that kills W, so that's 0. So that's the check that W is invariant under the action of y. So now I've got this non-zero vector space W on which y acts, and it just remains to pick a non-zero V in W that is an eigenvector for y. Then, as before, we have actually that yv equals 0, as y is nilpotent. That was the initial assumption. And so now we've got this, this vector, little v, it's killed by y, and it's killed by all of n. Hence, it's killed by all of v, as G is n direct sum the span of y. And there's the proof. Okay, so that's proved Engel. I'm writing C for complex numbers because that's what I'm basically assuming, but you don't have to look very far at that proof to see actually that's totally valid over any ground field. Okay, so that's Engel. So that was the getting a basis where G acts strictly upper triangularly. And then Lie's theorem, our hypothesis is instead that G is solvable, and we're trying to get a basis where it acts weakly triangularly. Okay, so let's go ahead and prove Lie, and the proof is very similar, so you should just line it up against the proof of Engel. So now, so just as before, you do an induction on n to reduce the general proof to checking the main step. So we have to just show that there exists a non-zero vector in V such that when you hit V by G, it lies in the span of V. And once you've got that, then you get this weakly upper triangular property just by induction on n, just like in the proof of Engel's theorem. So to do that, so let me just write down the hypotheses. We've got this subalgebra G of GLV, and we're assuming that G is solvable. And I'm going to use induction on the dimension of G, just like I did in the proof of Engel's theorem. So I guess now I can use the base being when dim G is 0. And now we're on to the induction step. We're trying to prove this main step statement by induction. And so we're assuming for the induction step that the dimension of G is positive. Now, G is solvable. G over G prime is non-zero, and it's an abelian Lie algebra. So just pick a codimension 1 subspace and take its preimage in G, so I'm just using the correspondence theorem, you get a codimension 1 ideal n of G. So that means that G is n together with the span of some other vector y. Okay, now n is an ideal. Since G is solvable, n is solvable, so I can just apply induction, the main induction on the dimension of G. So induction gives me that there exists a vector W non-zero such that NW lies in the span of that W. This means that if I take any x in n, x on W, it's a multiple of W, but of course that multiple is going to depend on x. So there's going to be lambda of x, some lambda in n star. Okay, so there exists such a lambda. Then I'm going to let capital W be the set of all little w in V. So the little w we picked earlier is one such vector, but there will be others. So I'm going to let capital W be the set of all such. Right, so because the little w earlier was one such vector, our choice of lambda ensures that this is not the zero subspace. Now I've got to show that YW, remember Y was this generator of the complement of n in G. I've got to show that YW lies in W, so that actually W is stable under the action of Y. Once we've proved the claim, the rest is easy. I mean, since we're over the complex numbers, we can pick a non-zero vector in W that's an eigenvector for Y. So we need algebraic closure right there. That's where we need algebraically closed field. Otherwise, this endomorphism Y of this finite dimensional vector space W wouldn't necessarily have an eigenvector. And then the line spanned by V, it's invariant under the action of Y, and it's invariant under the action of N, So it's actually invariant. And not G for capital G, German G. GV lies in the span of V as G is N direct sum C, Y. And we're done. Okay, so it's all reduced now to this claim. So to do this, this is now where we're actually going to find we need the field to be of characteristic 0. So to prove the claim, I'm going to take some x in this ideal N and some w in W. Right, so I'm trying to show that y times w is another vector in W. So we're going to need to apply y to W. We're going to need to show that x applied to it is lambda of x applied to it. But we can calculate this. This is the Lie bracket xyw plus yxw by the definition of module over Lie algebra. And now xy, that's inside N, right? So that acts as the scalar lambda of xy and w, and x acts on it as lambda of x. So we've actually got this guy, and we want this guy R. So we need to show that lambda of xy is 0. And then we're done. Okay, so we're getting close. Well, now what I want to do is I want to choose N maximal. So the vectors W, Y, W, y squared w all the way up to y to the n minus 1 w are linearly independent. And I'm going to consider the matrix of x acting on this basis. So I claim that it equals the following. So here's our basis, w, y squared w, y to the n minus 1 w. Well, we know that x on w is lambda of x w, right? So we know the first column. And star gives us the second column. It's lambda of x. Then it was lambda, let me see that second column. So we're acting with x on y w. So there's the lambda of x, yw, and then we get lambda times the commutator, that xy. And so I claim that actually what happens is that this matrix is upper triangular with lambda of x on the diagonal. And this follows by a simple induction. Just like star, you have to work out how x acts on y to the iw, and you find that it's lambda of x, y to the iw, plus stuff in the span of the earlier guys, w, yw up to y to the I minus 1w, right? So that's just a simple induction on I, just like we derived star. Hence, the trace of the endomorphism of W defined by the action of, the trace of, I need to name this subspace. Let's call this W prime. The endomorphism of W prime defined by the action of X. The trace of this is the trace of this matrix, and this is a scalar matrix. The diagonals all the scalars, and it's an n by n matrix, so that's n lambda of X. This is for any X in our Lie algebra n. And I can't use n here, can I? So that's annoying. So I've got to switch to some other letter because m was fixed from the beginning. Otherwise, it's all good, I think. So that should be an m. There we go. But this shows in particular that the trace of xy on W prime is m lambda of xy. If you remember, this is the thing we were trying to show was 0 to finish off the proof. But that's the trace of a commutator. So that's the trace of x acting on W prime composed with y minus the trace of y acting on W prime composed with x. And of course, the trace of any commutator is always 0. I mean, trace of AB is trace of BA for matrices A and B. So the trace of a commutator on here is definitely 0. So we're really nearly there. We've shown that m times lambda xy is 0. And finally, we've got to divide by m, which we can do because we're in characteristic 0. And that's the end of the proof. But just note right here, this uses characteristic 0. So that's why that assumption is essential in Lie's theorem. Okay, so there we go. I kind of went quickly through the proof of Lie's theorem and the proof of Engel's theorem. I think it's helpful to see those two proofs side by side. They're very analogous arguments, but Lie's theorem is harder because you first of all need your field to be algebraically closed to get those eigenvalues, and then there's this cunning little trace argument at the end, which is actually something that we see quite a lot in this stuff. Okay, so that's the end of chapter 1, sort of chapter of odds and bobs. We've spent most of the time kind of just really getting used to working with modules over Lie algebras, and you've seen lots of calculations actually with SL2 especially, where this universal enveloping algebra has been very helpful. And I've done quite a lot of multilinear algebra using tensor products and symmetric powers. And then at the end, I talked about nilpotent and solvable Lie algebras, and we proved Engel and Lie's theorems. Those are important. So moving on, the next chapter, I'm going to focus now much more exclusively on semi-simple Lie algebras. And we're going to start seeing root systems emerging out of those. So this is kind of the first step towards the classification of finite-dimensional semi-simple Lie algebras. So let's start this off. So remember, we're always working now over the complex numbers, and I want to recall that a finite-dimensional Lie algebra G is called semi-simple if it has no non-zero solvable ideals. So I've given you that definition before, but now I can start giving you examples of some. So we're in a position to prove the first lemma, which is a very useful criterion for showing that naturally occurring Lie algebras are semi-simple. So it simply says that suppose that G is a subalgebra of the special linear Lie algebra, so trace 0 endomorphisms of V under commutator for some finite dimensional V. And assume that V is irreducible as a G module. And so G acts irreducibly on the vector space V. Then the Lie algebra G is a semi-simple Lie algebra. Okay, so we're going to prove this in just a second, but let's just give examples to convince you that this is very useful. For example, it applies to SLV. Kind of almost a bit tautologically, it's totally obvious that V is irreducible as an SLV module. I mean, SLV, you can take any basis, not quite any basis to any other basis, but up to a scalar multiple, you can take any basis to any basis. So this lemma applies immediately to SLV. So SLV is a semi-simple Lie algebra. You probably already have noted, I think, that SL of V is a simple Lie algebra, so that's not too impressive. But it also applies, for example, to the symplectic Lie algebra SPV for dim V being even necessarily to have a skew-symmetric bilinear form and greater than or equal to 2, and it applies to the special orthogonal Lie algebra SOV for dim V greater than or equal to 3. So in those cases, you know that they are trace zero matrices. I guess we know the groups better, don't we? We know the symplectic group SPV, which sits inside SL of V, and the orthogonal group SOV, which sits inside SLV, right? Those were determinant 1 matrices. And for the groups, it's easy to see that V is an irreducible module, an irreducible representation for the group. That follows by, for example, you could use Witt's theorem to see that without any work. The symplectic group acts transitively on 1 spaces inside V by Witt's theorem. The special orthogonal group acts transitively on degenerate 1 spaces and on non-degenerate 1 spaces, both by Witt's theorem. And using that, it's rather easy to see that V is irreducible as a module over the group SOV. And that's good enough because G and G leave the same subspaces invariant. That was something we noted in chapter 0. Therefore, V is irreducible for the Lie algebra 2 as a consequence. Okay, so this is a useful lemma. From the lemma, you see immediately that all of these classical Lie algebras, SL, SP, and SO, are examples of semi-simple Lie algebras. And so those are going to be, in fact, our main examples moving forward. So let's see if we can prove the lemma to finish with today. So what I've got to do is I've got to show that all solvable ideals are 0. So let's take n to be a solvable ideal. And we're going to show that n is 0. Okay, but so since n is solvable and I'm over the complex numbers, I can apply Lie's theorem. Actually, I just need that main step from the proof of Lie's theorem, the first vector in that basis. It gives you a non-zero vector in V, which n sends V to some multiple of V. Well, let me write that out properly so that xv is lambda of xv for all x in n, and over here lambda is some functional in the linear dual of n. Okay, so that's what Lie's theorem gives us. It gives us this non-zero vector with this property. Now let's take y in the Lie algebra G and do our usual calculation. XYV is the Lie bracket XYV plus YXV. But since so x is so I should write x is in n here. So xy is in n, so that's lambda of xy v, and x is in n, so that's lambda of x y v. So this is just the same formula at the start that we were using when we were proving Lie's theorem. Now I've got to use that v is irreducible over G. Well, that means that any non-zero vector generates, right? We've got this non-zero vector little v, so it means that this is a cyclic vector. So if you hit v by the universal enveloping algebra, you get the whole vector space. But for the universal enveloping algebra, the monomials in a basis of G, they span the universal enveloping algebra. So this tells us that V has a basis consisting of elements like some monomial yi1, yin, v for yij's in G. Okay, so we pick some basis for G. The monomials, all the PBW monomials applied to V certainly span, and then you can just pick a basis inside that spanning set. So you get a bunch of monomials consisting of y's in G applied to the vector V, which give you a basis for this vector space V. And now, just like in the proof of Lie's theorem, you use star and induction to see that x in n acts in an upper triangular way on this basis, suitably ordered. So you need to order it so that longer monomials are later in your basis. So it means that x acting on V will look like some matrix, and down the diagonal, right, so just the way x acts on some y applied to it, it's just lambda of x of that vector, and then you get a scalar times some earlier vector, which is some commutator. So this matrix is going to have lambda of x down the diagonal, and then it's going to have it's going to kind of be upper triangular in this way. And this is for any vector x in our solvable ideal n. In particular, the trace of x acting on V is going to be the dimension of V times lambda of x. Oh, but hang on. We were assuming we were inside SL of V, right? So this trace is 0 by assumption, and we're in characteristic 0. So this actually shows that lambda of x is 0 for all x in n. Now what's up above? So maybe it's helpful to look at star again now in the light of this. So that right-hand side of star actually now we've shown that lambda is just, this functional lambda is actually simply 0. So the right-hand side of star, everything appearing there is simply 0. And this shows that if you take this vector v and you apply any y in G to it, and keep going by induction, any of these monomials, x will act as 0. So now it follows, I'm explaining this a little bit badly, that any x in n actually has matrix 0 when acting on this basis. But that means that actually x is just 0, and that shows that n is 0, and so indeed G is semi-simple. End of proof.